Yeah, okay. So we were looking at the particle in a box problem to see, to understand the energy quantization. So we considered a one dimensional potential well EP represents the potential energy, and we started with a time independent Schrodinger equation. Okay. So in the first place, when the particle is inside this box, within these boundaries it is free to move, and so there are no boundary conditions imposed on the particle when it is moving inside this so called you can also call it a potential well. So inside this box, flat band potential is imagined. I also said that this is not a gross approximation because most of the solid has empty space. So the particle is actually free to move within certain domains. Okay. Then the whole why did we start looking at this whole process? Okay, from this equation what the information that we get is the electron can take all energy states. There is no restriction on the energy states that an electron can assume in this K space. Now, is that the reality? The reality is something else, especially when the problem came to explain the experimental specific heat values, electronic specific heat values, which were almost one order less than what the theoretical values showed. Then there was a need to look at the so called free electron theory. That means the concept that all the electrons belonging to all the atoms in a solid do contribute to a given physical property, especially a physical property like electrical conduction, thermal conductivity, or electronic specific heat. So somewhere something is wrong and some corrections need to be made. So we started with the assumption that we started with the assumption of the wave nature of the electron. Electron can have both the particle and wave nature, and so we started applying the quantum mechanical concepts, right, with the simple quantum mechanical equation, the time dependent equation. Yeah, this what let me just quickly go through all that we have seen in the last two classes. When there are no boundary conditions, this equation holds good, and this also leads to the free electron parabola, is it not? And what we did was, so this is a quick recap of what I've done in the last class. So when we apply the boundary conditions, especially when the electron encounters these barriers, potential barriers, and when you try to look at the probability of finding an electron at these barriers and in the region in between these barriers, okay, there is a finite probability of finding an electron in between these potential wells. At the barriers, the probability is 0. Okay. Now, starting with that, so we looked at this one dimensional time independent wave equation. I also said we are starting with this simplistic time independent equation, so that we are not considering any other perturbations the electron would have undergone, right. That becomes a little more complicated case. But in reality, even though you are saying that an electron is free in a solid, I keep asking the same question, right. So, what is the definition of this freeness of this electron? Electron always has a potential that it experiences from the positive ion core. Okay. So, it is always under the constant potential of the positive core. So, it's in one way it's never a free particle. Okay. So, we started with this equation, and we applied the general solutions to this equation, and we applied the boundary conditions at the two ends, where you have when x is equal to a and x is equal to minus a, these boundary conditions lead to the following solutions. And here your K A is equal to n pi, and so you have a solution which shows that okay. So, this L is the length of the box. So, for all practical purposes, I have replaced A by L. L is the length of this box. Okay. Now, we have say psi 1 . So, this itself shows that the energy now is so that is very clear. Okay. So, you clearly see the energy quantization here. Okay. Now, so what are the allowed wavelengths and the allowed wave vector numbers in this particular case? What are the allowed wavelengths? Is it not? And allowed wave vectors, you have it there. Right? Which means okay. So, you have discrete energies of the electron that can be assumed. You also have allowed wavelengths. You can call it instead of psi here, this should be lambda n. Okay. So, that gives the allowed wavelengths and the allowed wave numbers. Okay. Now, so what is the for n is equal to 1, n is equal to 2, n is equal to 3. So, for n is equal to 1, the wavelength is energy is it not? For n is equal to 2, is L, and energy is yeah, and for n is equal to 3, the wavelength is 2 by 3L, the energy is E3 is 9 E1. Okay, this is quite interesting because what we have seen next after this. Yeah, so that's what I have written on the board, and that's where we are. No. So, the probability of once you have this, you should be able to find out the probability density of finding an electron at these different levels. And we have seen that, right, the probability of finding an electron as you move up the ladder at the higher n values is much more towards the boundaries also, whereas in the case when n is equal to 1, right, the probability of finding an electron is always there only in the middle of the well, and this sort of extends towards the boundaries also as we move up. 1. Second, the quantum mechanical probability of finding an electron at lower n values is much smaller compared to what you would expect in the case of classical physics. But as you move up, as you go to higher numbers, n is equal to 8, 9, 10, right, these two probabilities, the quantum and classical probabilities, almost become equal. So, what does it tell us? It tells us that, of course, the electronic levels that are close to the core, the positive ionic core, are more discrete, and as you go up the ladder at higher n values, you would have almost free electrons. So, the system is tending to be more of having a classical nature. Okay, what does it mean? How do we understand this mathematically? So, I have also mentioned that towards the end of the class. Of course, you also have to look at the entire scenario when the actual solid is formed. Okay. Now, so we have all these discrete levels, and from what we have seen until now, we can sort of sketch a diagram in this way where you have these discrete levels, and probably at the higher n values, okay, you start seeing this continuum. All right? Okay. Now, so you have an atom, you have several atoms that you bring together and the solid forms, and these individual discrete levels start forming into the so-called energy bands. Okay, you have an energy band corresponding to these different levels, and in a solid, if you start filling the electronic levels by not violating the Pauli's exclusion principle, you end up filling all these states, move up the ladder, and the topmost filled level is termed as a Fermi level. Okay. The topmost filled electron level is called the Fermi level. The Fermi level is defined as the topmost filled electronic level at 0 Kelvin. That means at 0 Kelvin, the probability of filling states below this so-called Fermi level is always 1. Okay? The probability of finding an electron above this level is 0. Now, what happens at other temperatures other than 0? Okay. So, it all boils down to probability of so we can start with the Fermi-Dirac statistics. Where I write down the expression. This expression of course represents the probability of finding an electron also. Okay. One by 1 plus exponential E minus EF by kBt. Kb is the Boltzmann constant, T is the temperature. Okay. Now this is a very useful expression to start with, the Fermi-Dirac distribution function. I mean, this plays a very crucial role in understanding many things. Later, we will also use this expression to find out the number density of occupied electronic states. There is what is called electronic density of states, or simply density of states, that give you information about the number of occupied electronic states in a system. And it is this number that determines the nature of a system. Okay, we will come to that. But starting with this, so this gives an expression between the probability of finding an electron and what you understand from this equation here. Now you see, let us apply some conditions. Let us say what happens to F when E is less than EF? For E less than EF, F is equal to 1? Yeah. At T is equal to 0 K always. Okay? We are at T is equal to 0 K, for E less than EF, F is equal to 1. And okay. Now, so in terms of probability, I plot F of E versus energy, and I can also take the third condition and see what happens when E is equal to EF. E less than EF, F is equal to 1. For E greater than EF, F is equal to 0. Yeah? Now you try to plot this. So I have EF there, so okay. Well, this is known. This particular condition also tells you that what about the temperature dependent in terms of finding out the probability for T values greater than 0 Kelvin? All this is at when T is equal to 0 at absolute 0, minus 273.12 degrees centigrade. Okay. Now you say you take T1, T2, T3, you start heating up the system. So when you start heating up the system, what you expect is, look, no matter what, the probability of finding an electron between, so if this is the topmost level, the topmost field level, and you also have an empty band above it. Okay. So in real terms, we call it a filled band and an unfilled band, a filled or an empty band. So you can actually excite charge carriers, okay, across this gap. These gaps do form in solids. Now, because we already have seen the discreteness in the EK diagram, is it not? Remember that? In the EK diagram, once the energy quantization happens, even though the parabolic nature is retained, you see these are the gaps that appear between the different zones. I also said that is a first zone, etc. So this I can show you here. Yeah, that's what it is. Now you see the dashed curve still represents the free electron parabola, right? So the EK diagram representing the free electron parabola, but with energy quantization, what you see is, you see the discreteness. So this is plotted in units of pi square h cross square by 2 ml square. So wave functions are only certain energies can fit into the solid. This is very clear. And also, this is a EK diagram of an electron in a what is called a confined potential, where now you see the clear, energy quantization. Now between these levels, this is the so-called the forbidden. These are the forbidden gaps in the solid. Okay, so the gap between the top two levels, the filled level and the one unfilled level above it, is nothing but the band gap. If you are talking in terms of a semiconductor or an insulator, and this system becomes conducting when there is no gap between the two levels, the two bands rather. If the valence and the conduction bands overlap, right, you have a free electrons moving inside the conduction band even at ambient temperature. Okay. Now, you see these are the Brillouin zones, the two-dimensional zones. What you see, the interior square is the first Brillouin zone, okay, with the limits of pi by a to minus pi by a on the x axis, pi by a to minus pi by a on the y axis. Similarly, the second zone, right, 2 pi by a to minus 2 pi by a on x and y axis. Right. Now, you imagine in a three-dimensional solid how these zones look like. I'll show you some pictures of how exactly a three-dimensional Brillouin zone looks for a simple system to a complicated system. Because when in reality, when a solid is brought down in size, right, I said there are going to be serious changes on the surface. I said there is surface restructuring, is it not? Remember that? Surface restructuring means the modification of the crystal structure on the surface of a particle. So, in one way the surface atoms, right, crystallographically arrange in a different way compared to the atomic arrangement inside the bulk. This is very interesting. So, when these changes happen, to some extent the electronic band structure also is affected, and the so-called Brillouin zone, these Brillouin zones also, the three-dimensional Brillouin zone, you see a complete transformation in some cases. So, you see changes in the crystal structure, the band structure, and also the way the Brillouin zones are constructed between the macroscopic bulk and the nanoscopic material. Okay. We will come back to that, and I have to highlight the importance of these boundaries. Okay. See, normally most of these things are covered in a regular condensed matter physics course, but since most of you are may not be familiar with the solid state physics concepts, I am spending more time on these concepts to make you get familiarized with all these important concepts. Without this, you will not understand what is meant by the so-called quantum confinement. Okay. Right. Now, so we have seen this also in the last class. So, as we can, yes, that is what it is, and energy in terms of units of pi square h square h cross square by 2 ml square. Okay. Now, that is now you see what happens if you increase the temperature. What you will see is it's very clear that the probability density does not have a dependence on temperature. At whatever the temperature the system is, the probability of finding an electron is always 0.5, half. So, at a temperature T1, what you would see is something like that. And this is at say T1, and at T2 at a little higher temperature. So, what you see, and at this is your T3, this is your T2. What do we understand from this? Now, look, so this is your KB T1, and I have KB T2, and progressive increase in energy. Let us say this T1 is 300 Kelvin. 300 Kelvin is typically the room temperature value, which is equal to 26 milli electron volts. So, at room temperature, the amount of thermal energy that the electrons experience is 26 milli electron volts. Okay. So, this is a case at 0 K. Now, as I increase the temperature of the material or a system, what you see is you still have a probability of finding, right, finding it at 0.5. Okay. But in terms of explaining the discrepancies with respect to the specific heat measurement, what we can say is only within an energy limit of kBT, right, you will be able to excite electrons. Yeah, before that I should say, look, now what matters in a solid is when the solid forms, the band formation happens. What matters in a solid is for us to see a physical property, you must excite the electrons across the Fermi level, EF. Then only you can say a given process is on. That means in order for conduction to happen, the electrons in this band should move across the Fermi level. And similarly, if these electrons in the lower bands have to participate in a conduction process, they have to move across the Fermi level, because otherwise there is no process of conduction. If we are taking the process of electrical conduction as an example. But now at 0 Kelvin there is no thermal energy provided to the system, and you do not see any carriers getting excited across this level. Okay. So, in a normal conductor, by virtue of the overlap between these two bands, okay, so the Fermi level is within the two bands that overlap. So, you have a completely filled band, but the one above it, which is unfilled band, overlaps with this one, because the electronic density of states in the case of conductors, metals, is so large that this overlap happens. There is no problem, right. So, the density of electronic states is lower in the case of semiconductors, right. So, the bandwidths are smaller, and hence the bands open up. So, especially there is a good amount of separation between the top two levels. So, once the top two levels are separated by a certain gap, this gap has energy. You understand what I am saying? So, I have a lower band which is filled, I have an upper band which is empty, I call it filled, empty. Of course, these are called the valence bands and conduction bands. Conduction can happen only when electrons are excited into the conduction band from the valence band. But in the case of metals, there is an overlap between these two bands. And if you take the principle that any carrier excited across the Fermi level only participates in a given process, and that happens in the case of a metal with ease, there is no problem. I do not have to really increase the energy in order to make the electron, right, make a transition or make a jump from the valence to conduction bands. So, if you call this the Fermi level, Now, what this means is, now imagine the system. Yeah. Okay, this is the total energy. We have seen this already, and this is basically a comparison between the free electron, where the electron can assume all energy levels, an atom on the extreme left side, discrete energy levels, and a solid where you have bands and there are gaps between these bands, is it not? So, you start with separate atoms that are brought together, and all these levels, this is an example where the 1s and 2s levels start forming into bands and leaving a gap between these levels. And I have also shown this in the last class, the way the bands form in a solid, and I also said the importance of the equilibrium interatomic spacing. Okay. Okay. Of course, the Pauli's exclusion principle limits the number of electrons within with the same energy. So that's the reason why the band formation happens. If you go this way, finally we reach a point where, right, the solid forms, and these are the topmost levels. So the level up to which electrons are filled at 0 K is called the Fermi level, and in the case of conductors, you have the valence and conduction bands, the top two levels, the filled and the unfilled bands overlapping with each other. The Fermi level is inside this, overlapped bands. There is no problem. So the electrons are free to move. But in this case, if electronic conduction has to happen, the electron has to be excited to the empty state from the completely filled state. Remember, if you have a completely filled band, okay, there is no conduction. A half filled band gives rise to conduction. A completely filled band, there is no conduction. So a completely filled band in the case of a semiconductor, right, you can, this is like an electron reservoir. So you can excite the electrons from this reservoir into the upper band, which is called the valence band, and of course the transition of electrons, excitation of electrons by various means of energy. It could be thermal energy or photon energy, any other form of energy. So if I provide thermal energy or energy in the form of photons, I can excite some of these electrons into the upper band. Now, as the electron moves from the valence to conduction bands, it is, what is the energy required for this electron to move from this conduction band to the valence band to conduction band? That energy is determined by the energy of the Fermi level. That is why I said that in the other class I was asking you, what is the significance of this energy? Oh, it plays a very important role. So unless the electron gains an energy equivalent to the energy of the Fermi level, right, it will not be able to make a transition. So unless that happens, obviously there is no conduction. So if an electron has to go into the conduction band and move, right, I must provide that much of energy for the electron to make a transition across the Fermi level in order that it moves from the valence band to the conduction band and then gives rise to the property of conduction. Now that energy is determined by the energy of the Fermi level. Now what happens at higher temperatures? So at say T1, you are providing the system this much of energy. So which means only those electrons with the energy corresponding to the Fermi level get excited and participate in a given process. Not all electrons, because now we have we have also seen that the continuum is happening there. Okay. So now your Fermi level is somewhere there, say. Okay. Now these electrons can easily be excited because these electrons in the upper bands are already at a higher energy level. But what about the electrons in these bands? Obviously, if you go back and look at the classical theory says that you account for the total number of electrons in a solid belonging to any level, 1s, 2s, 2p, any level. All of them should participate in the process of say conduction. But that is not true, because only electrons within KBT would participate in a given process. Now, what does it mean? This means the electrons in the lower energy states, means those electrons that are close to the nucleus are much more bound tightly, right, and these levels close to the nucleus are also much more discrete compared to the levels as you move up. Now, we have seen that n is equal to 6, 7, 8, 9, 10, right. The probability densities of the classical and quantum particles look the same, there is no problem. So, this is a key for understanding the whole thing. So, KBT1 means you are providing 26 milli electron volts to the system, 26 milli electron volts, and if this is 3000 Kelvin, it is 1 order more. Now, in a solid, let us now imagine, so as I increase the temperature, I am giving more and more energy to all the electrons, obviously. First of all, the electrons start vibrating more vigorously from their mean positions. That is one. There is a lot of contribution to the phonon spectrum. Now, these electrons, which are close to the Fermi level, they already possess an energy with which they can make an electron to transit via the Fermi level, absolutely no problem. But what about the electrons in the other levels? So, if you have to calculate, if you have to say that all these electrons in all the different levels have to behave like classical particles, because it all started with applying the Maxwell-Boltzmann statistics, where you are considering all the particles as classical particles. So, if all the electrons in the system have to behave like classical particles, what is the energy required to be given? So, the typical Fermi energy of say copper or gold, it varies anywhere from 5 to 9 electron volts. So, let us take the Fermi energy of 5 electron volts. Okay. Now, when you have the Fermi energy of 5 electron volts, so suppose we are providing the system some thermal energy, and this thermal energy is sufficient to excite the carriers from different levels, say across the Fermi level. Okay. So, if T1 is 300 Kelvin at room temperature itself, the system has certain energy, 26 milli electron volts, no problem. Now, you start increasing the temperature, because I want more and more electrons from different levels to participate in this process of conduction. Okay. But the energy that I need to provide is 5 electron volts, because that is the Fermi energy, because every electron has to move across the Fermi level in order to participate in the process of conduction, otherwise no. Okay. So, what is your TF? With a Boltzmann constant value of 8.85 into 10 raised to minus 5 electron volts per Kelvin, what is the the Fermi level has an energy which is called the Fermi energy, and the corresponding temperature scale, which I call it TF. Now, we can calculate for 5 electron volts and the Fermi temperature turns out to be? I can give the suffix F in both the cases. So your TF is 5 by this value, which is 10 to the power of? Yes. So if I am providing thermal energy to this system, in order that all the electrons in all the levels participate in the process of conduction by moving across the Fermi level, I need to provide this kind of thermal energy to the system, 10,000 Kelvin. At 10,000 Kelvin, obviously all the electrons in all these levels become free electrons, and then they just move across the Fermi level, which is an impractical proposition, because most of the solids melt below 2000 degrees centigrade. Right? Only refractory elements, refractory solids have very high melting points. This never happens. So what we understand from this, there is no way electrons belonging to all the atoms participate in a process like conduction or electrical conductivity, thermal conductivity, or even electronic specific heat. Now we can go back and understand why this is mole per Kelvin, which is 0.2 joules per mole per Kelvin between theory and experiment. It's very simple. Experimentally, for the given temperature range that is used to do an experiment, if you have done an experiment say up to 1000 Kelvin, right? So your KBT is about how many milli electron volts? So at 1000 Kelvin, if I have done this specific heat electronic specific heat experiment, so now we have the actually classical model did not fail at higher temperatures. So the specific heat measurements done on different systems agreed well with the specific heat values of most of the systems only at higher temperatures. Only at lower temperatures there is a problem. Something like lead, this for diamond. You see, at high temperatures, this is very clear now. At very high temperatures, the particles become classical particles. They can participate in a process of conduction because you are exciting these carriers across the Fermi level. So the essence of all this is this particular energy value. So the solid which forms into different bands, the electrons in a solid form into different bands, right? You have the lowermost level to the uppermost level. The uppermost filled level is called the Fermi level, right? So the level that this separates from the filled from the unfilled levels. In order for an electronic conduction process to happen, or even for an electronic excitation to happen, you need to provide energy for electrons to be pumped up across the Fermi level, and the energy that is required for that process to happen is kBTF. So those electrons having this particular energy can only be excited and are made to participate in a process of conduction, which also applies to the specific heat also. Now we now can sort of judge why there is a clear cut difference between the experimental and theoretical values, because in this case you have considered all the electrons. Okay. Each electron has 3 degrees of freedom. You have say n electrons, so 3n entities, right. The internal energy is 3n kBt, and your CV it's as simple as that. It just depends on the number of entities present in a solid. There is no temperature dependence there. That is where the further corrections have come. Okay. The temperature dependence plays an important role. So that is where the Debye temperature concept has been brought in. Okay. Then the Debye-Einstein model. So what is the Debye temperature? Debye temperature again plays a very important role in trying to describe the properties of solids. What is a Debye temperature? In simple terms, a Debye temperature gives you information about the stability of a solid. So each system, each element, each compound has a certain Debye temperature, right. So when a system is specified with a certain value of a Debye temperature, that means you can say the system is stable until that particular temperature, and beyond the temperature the system tends to be unstable. So you can take it that way when you are talking about it is represented by this capital theta value. Okay. All right. So is this clear now? Now you know why these discrepancies, right? And you also have realized the real importance of the Fermi energy. Okay. Any questions? You take any basic book on solid state physics, all this will be there. Charles Kittel, Ashcroft, Ali Omar, everything is there. And if you follow the class carefully, then it's good. Okay? All right, we'll see you tomorrow. I'll see you tomorrow.